In this lecture, we will be discussing fundamental types of variables. They are essentially objects, and we have integral types and floating point types, and it is further subdivided into Boolean, enumeration, character types, and integer types. Before the discussion of these fundamental types, I need to discuss the new IDE, because the code blocks did not have the color theme which is pleasant to the eyes. It is causing way too much glare for some students. So what I've done is I've went to this website, sourceforge.net/project/Orville dev cpp, and if you just search for de dev c on the internet or Google it, you will find the integrated development environment, which is much more pleasant looking. So you just download it and install it, and it will give you an option of different color themes which could be possible. So for most pleasant color theme, I've selected obsidian or black color theme. You can select any color theme you want. So this is the dev C++ 5.11. I have installed the latest version, which is available on sourceforge.net, and what I will do is I will just go to file and new, and I will click source file, or just press Ctrl N, and you will get source files. And then I will just type the basic C++ file, right? Include IO stream, and then I will be using namespace standard and integer main void, and then I will be writing the last line as return 0. I mean, that's the basic structure of our pretty much every C++ program we are going to do in this course. So I'm going to type here, and I will just save as let's make a name of, let's say, E13.cpp, same thing as we did before. Make sure the extension is correct and save. And then to compile this thing, I will just go to execute, and I will press compile and run, which is F11 over here. So, and then it will show up the command prompt window for any output the program might have. Since it's essentially an empty program, it will not show anything. So coming back to our original topic of fundamental types. So fundamental types are integral types, essentially whole numbers, and floating point types are essentially numbers with decimal points. Actually, these fundamental types are actually a subset of complex numbers, and complex numbers have the real part and the imaginary part. But in this course, we are only going to discuss the real numbers, and for complex numbers, you need to include the complex header file or any header file which can handle complex numbers. So now, right now, we are only concerned with real numbers, and real numbers can be whole numbers and floating point numbers. So I mean, essentially whole numbers include 0, and positive numbers and negative numbers, such as 123 or 100 or -256 or 0 or -512, and they are called integers. So we will be declaring those integers using int declaration as type declaration, and we can also have a there are other types of integers as well: short and long, and unsigned short, and unsigned integer, and unsigned long. These are, if you have declared them as unsigned integer, that means that that variable would be carrying, or it's allowed to carry only 0 and positive values. Actually, they are related to how much memory they occupy, and as we go along in this lecture, it will become much clear what we mean by that, because the computers we are using are actually quite powerful, and they have lots of memory. I mean, let's say if you have a basic computer, it might have 4 gigabytes of RAM, or maybe 8 gigabytes of RAM, and the hard disk would be around like 512 gigabytes or 1 terabyte. But if you are programming embedded systems, if you're programming microcontrollers, they might have very little memory. They might have memory in tens of kilobytes, and in those environments where you have to use the microcontrollers or small computers which have very little memory, and you have to control some physical processes such as some industrial processes, there you have to be really careful in using the type of variable, because let's say if you want to store really small numbers, you really don't need to declare them as long, because it probably is going to occupy like 8 bytes of memory. And let's say if you have like 1000 variables of type long, that is like 8 kilobytes of memory just for the storage. And there would be some other overhead associated with these variables, and it might occupy even more memory. So if you have like 32 kilobytes of memory for the whole computer, let's say you are using some really basic microcontrollers with built-in memory, then you have to be really careful in using the type of variable you are using, and do not allocate more than the required memory in that scenario. So integers are essentially whole numbers, and they are essentially decimal numbers, negative numbers, positive numbers, and integers are essentially whole numbers, and any numbers with decimal part, including the fractional part, they could be negative, and they are rational numbers, because they can be represented as a ratio of whole numbers, such as 10 divided by 3. And they could be irrational numbers as well, where the such as pi or under root 3 or under root 2. But the problem with computers is that it has a finite precision. I mean, it has finite memory. That means it can have even finite number of states. So even irrational numbers, if you are using irrational numbers such as pi or under root 2, you have to approximate them with rational numbers, such as, I mean, you cannot go on for infinite precision as with number pi. It's depending on the type of variable you are storing that pi in, you would be limited to, let's say, like 5 or maybe 10 decimal places allowed. Depends on what kind of variable you are using. Let's say I'm using, we are going to discuss that what is the maximum precision allowed in that variable. Let's say I'm using float. There might be fewer decimal places available, and double, and in long double I could have even double and even more than double the precision available. But even then, the amount of precision is finite. You cannot have infinite precision in a computer, and that will lead to some round of errors. We are going to demonstrate that as this lecture goes along. I think that will be in lecture number 7 or 8 maybe, so we will visit that. Okay, so integer numbers, they are used to count something, such as how many people are there in a team. In a cricket team there are 11 players, so that is a kind of exact, and people can go and count them, right? And rational numbers, such as with decimal part, I mean like fractional part, such as 12.325, they are used for measuring something. Integers, they are essentially exact numbers. I mean, they are essentially whole numbers. And rational numbers, such as floating point numbers, they can be approximate. I mean, they can be an approximation of even let's say you have like 4 decimal places available, and the measurement you did of some furniture maybe, and that was like 12.32579 feet, but you need to approximate it to lesser number of decimal places, because you have finite precision due to the finite amount of memory available for the storage of your variable. So integers are used for counting, and they are supposed to be exact, and rational numbers are supposed to be approximate. I mean, they are not exact. I mean, they could be exact, but sometimes we have to approximate. So that means that these two scenarios, they are reflected in computer storage as integral types and floating types, depending on how they are stored and manipulated. By that I mean that these two numeric data types, I mean the integral types and floating point types, I mean they actually represent two different classes of numbers. And the floating point refers to the scientific way to express numbers, such as if you have a number like 1 2, I mean let me type it out somewhere. Like if you have a number like 1 2 3 4.5 6 7 8 9, I mean you can represent in multiple ways. I mean you can represent it as the number as it is. I mean let me type it over here. let's say I have a comment over here, and what I'm going to do is I'm going to type a number, because 1234.56789. I could represent this number as 1.234567889 into 10 to the power 10 to the power 1.234, so that's 1200, 1000, 10 to the power 3. Okay, so I mean that means that it could be represented like this, or that means that the floating point number, this is a floating point number, okay, because the decimal point actually floats. So that means that this number can be represented like this, and it can also represent like this. So floating point numbers, I mean, we are going to discuss how they are actually stored in the computer, and that determines that, let's say if you have a 4-byte floating point number, some bytes would be associated with this part, that the whole number part, and some bytes would be associated with this fractional part, the decimal part, and some bytes would be associated with the power of 10 part. That means that if the number of bytes associated with, or the number of bytes used to store the decimal part is limited, it might be possible, I'm going to demonstrate that as the lecture goes along, it might be possible that the floating, that variable might store something like this. That means I'm not saying it would not have that much space. It's possible that it might be limited in the amount of bits associated or amount of bytes associated with this part. So it might be compelled to, because it can only store the finite amount of precision, so it might be compelled to store these last 3 numbers and round it off to this. Okay, so that means, or let's say if I have another number, let's type another number, something like 0.000986765. If we type this number, it is possible that the computer stores this number not like that, but with this, the whole number part, and 8765 into 10 to the power 1 2 3 4. How many spaces are the 1 2 3 4? Okay, 10 to the power minus 4. So that means the computer would store this as a floating point number. It might be storing the whole number part like this. It might be storing the fractional part, and it might be storing the power of 10 part separately, and depending on how much number of bytes or bits it's going to allocate to storing these 3 separate parts of a fractional number, it depends. It might be possible that it will, or probably may, round off the numbers at the end of the fractional part, because it might have some finite precision. So that means that all these alternatives are obtained by letting this decimal point float among the digits. So, and using the exponent on 10 to count how many places it has floated to left or right, or to the left or right. That's why we call these numbers as floating point number. Okay, so floating point number, coming back to that diagram, the floating point number can have like 3 different, depending on how much precision you want. This is the least amount of precision. This has the double as much precision, because this one is probably going to use 4 bytes. This one is going to use 8 bytes. I'm not so sure. I think it's 16 bytes or something like that, but be really careful if you're using some computers with small amount of memory, because they can fill up the memory really quickly, these large types. If you have a desktop computer with tons of like RAM, like 4 or 8, maybe 16 gigabytes of RAM, then you not need to worry if you're writing a small programs. But in smaller computers and smaller microcontrollers, you can fill up the memory really quickly with these large variables, because they are going to use more space. Okay, so we have, like, let's count them: 1 2 3 4 5 6 7 8 9 10 11 12 13 14. We have 14 different fundamental types here. We have like 1 2 3 3 floating point types and 11 integral types. I mean, they're essentially whole numbers, all of them. I'm going to demonstrate what they mean by that. They include Boolean type for true and false, enumeration type declared with enum keyword, 3 character types, this thing is going to be used most often, and there are like 6 explicit integer types. I mean, the most commonly used are Boolean, for true and false, and 1 and 0, and character, and integer, and double. I mean, these are the most common we are going to use. Floating points, so I mean, I have just explained that. I'm going to demonstrate that in a moment. So the first thing we need to look at is the Boolean type. A Boolean type is an integral type. They can have only one of the two values, false or true. False represents 0 and true represents 1, and they are stored as integers 0 and 1. The Boolean type in the C++ is named bool. So if you want to declare an integer, you write int and the variable name. If you want to declare a Boolean type variable, you just write bool and the variable name, and that's it. One more thing you need to remember is that Boolean type, true type, actually means 1, but any value greater than 0 is also treated as 1. I'm going to demonstrate that in a moment. So let's write our first program to test and see how these Boolean types actually work. I'm going to delete these numbers because I'm going to revisit them when I talk about the floating point numbers. Okay, so this is our first program. What it's going to do is it's going to print the values. I mean, this is just a comment of a Boolean variable. Okay, so this is just a comment. Compiler is not going to look at it because it is being preceded by double forward slashes. Okay, so we need to declare the variable. We just write bool, such as let's say if you want to declare a variable of type integer, you just write integer a equals to 12, and that's how you declare and initialize the variable. Similarly, if you want to, just comment that we're going to develop the concept for Boolean type variable. So let's say we have a variable type bool, and I name that variable as flag. Just a name. You can just write your own name if you want to. And I write false. False means 0. And I write cout, and the statement, the output operator, and the string returns beginning right here. And I write flag is, and that's it. And I write flag. That means this is just a statement which is going to be printed, and here the value of that variable is going to be printed just like we did in the last lecture. So coming back to here and just make a new line and L and see what we get. So to that I need to go to execute, and I just click compile and run. So here it is. It says flag is 0. Process I mean, these lines are just for dev C++ format. Flag is 0 and process executed after so many seconds with return value of 0. That means it's executed successfully. And let's try another thing. Now we just update the value of flag. We just write, or just re-update it, no problem. We just write flag equals to true. That what we did was that initially the value of this variable is false. Now we have updated or written over the value so that the new value of flag is now, I'm going to write cout, I'm going to write flag is now, and I'm going to write flag. That means whatever the last value of flag is, and I write an L, and let's see what we get over here. So I go to execute and I say compile and run, and that's what we have over here. Flag is 0. I mean, okay, so flag is 0. I mean, false means 0, right? It was false, and we printed flag is, and that is flag is, and the value of flag is 0, and flag is, and then we updated the value flag equals to true. That means flag is now, from here it says flag is now 1. Another thing we need to do is, I mean, they are essentially integers. They only allowed like two values, 0 and 1. And let's say if I write flag equals to 0 and flag equals to 1, essentially they are integers. So I'm expecting that we get the same result as we did before. So what we get, flag is now 0 and flag is now 1. So same result as before. So you can I mean, essentially they are integers. So I mean, only allowed like two values. Let's say I write flag is 0 and flag is 123. This value is greater than 1. This is sorry, this value is greater than 0. And watch out what we get. If we execute and compile and run, see what we get. It says flag is 0 over here, flag is 0, and let me over there. Okay, flag is 0 and flag is 0. That's how it's printed over here. And I say flag is 123. This value is more than 0. It says flag is now 1 because flag is only allowed a 0 and 1 value. So any value greater than 0 is treated as true or 1. I mean, logical true. If you've seen logical expressions before, you might understand it, but we will revisit logical expressions because they are really important to decide where the program goes. Let's say if you have to make some kind of a decision, if this decision is true, then do this thing. If this decision is false, then do something else. We are going to discuss that after we finish this type discussion. So let's try what we get if we put a negative value minus 123, or you can just put minus 512. Let's see what we get and see what we get over here. Still says flag is now 1. So that means any value other than 0 is treated as true. Not a good practice. I mean, make sure you are only allocating or you only assigning the true and false statuses only, not any other numeric values, because the reason why is treating it as 1 and I mean this thing is false is this thing is false or 0, that is being treated as 0, but any value other than 0 is not being treated as 1. So I mean not a good practice to do that, but you can understand the behavior. Coming to the next type is the enumeration type. I mean, we just declared with enum, and this is useful because these are Boolean character and integer types, and these floating point types, they are essentially predefined types in C++. But enumeration type allows the programmer to define his or her own special data type. They are behind the scene. They are essentially integer constants. Going to explain that in a moment. What we mean by that? They are actually more ways to define your own type, such as if you want to use struct. But now that struct is not that often used, you can use classes, class definitions, and make objects on those. So that's the most powerful way to do that. You can have your own data, whatever that might be, and the functions associated with that data associated in a same container. So classes and objects, they might come up after midterm. But first, if we want to develop your own, or if you want to define your own simple data types, simpler kind of user defined type. So enumeration type is an integral type, okay, and it is defined with this syntax. I mean, let me type it as a comment over here. I'm going to, because we have discussed Boolean, I'm going to delete that. And now it's going to be defined as you write enum. Just a comment right now. I'm going to explain that type name, and then you, if you want to, you have to write a enumerator list. Enumerator list happens here, and then you enclose it with curly brackets, and then you press the semicolon, end of statement. So that means that in this C++ language, enum is a C++ keyword, and type name stands for an identifier that names the type being defined, and enumerator list is they are essentially list of names for integer constants. They would be numbered from 1 to whatever number. I'm going to demonstrate that in a moment. For example, let's have some definitions over here. Let's say we could have let's run this thing, not run this thing, I can just write enum and just, I mean, that's not a comment really. I mean, you can just write enum and semester. Okay, and I'm going to enclose what semesters are there. So I'm going to write fall, spring. I mean, it's a good practice because they are essentially character integer constants behind the scenes, 1, 2, and 3, and we can, or maybe 0, 1, 2 if you want to. It depends really. So they are essentially constants. So the good practice for constants or integer constants is to write their names as capital letters. And let's see, spring, fall, spring, and what happens after spring? It's summer. Okay, so we just write, oh sorry, I think we have the bracket, and that's it. So we can now declare two variables of type semester. I mean, just as we before, after, just like in previous lectures, we did integer a equals to 12. That means the integer is a a is a type of a is an integer and it carries a value 12. So similarly, now we have our own type. So we have just defined it, and it can contain these three values. So what we do is we can declare our own variable of type semester. If I just write semester and I declare two variables, s1 and s2, and then I assign the variables the values s1 using the assignment operator equals to sign. S1 equals to spring and s2 equals to fall. So that means now this s1 and s2, they contain these two values. Okay, so what we can do is, I mean, we can run some checks or anything if you want to. So if I write an if statement, I've not discussed the if statement yet, but it might be usable here in this scenario. Let's say we can just write if s1 equals s2. That means if s1 is not, I mean, this thing, a single equals to operator is an assignment operator. It assigns this value or whatever is here to this variable. If I want to check whether this thing is equal to s2, then I write equal to sign twice. That means this is a logical expression. It might be true, it might be false, we don't know. So but if this thing is true, that means the result of this thing is true. Let me demonstrate that in another file, so that we come back here, because this is might useful. Let's write another file. I think we have to include iostream, same thing, and using namespace standard and integer main void, and then brackets, and then just write return 0. I mean, that's a basic part you have to write again and again. So let's make it integer a equals to 10 and integer b equals to 20. So if I want to check whether a and b are equal, essentially they are not equal, but let's check. If a equals b, I cannot write single equals to sign because that's an assignment operator. I want to check whether a is equals to b. Then if a is equals to b, then I mean, if I want to run the single statement, I don't need these curly brackets, so I'm going to delete that. If a equals to b, then cout these two variables, or I can just are equal. Okay, and L, and that's it. So if they are not equal, then else what will happen? Else cout these two variables are not equal. Let's save this thing. And what was the last example I saved? It was example 13. So let's make it example 14.cpp, and let's try to run this thing. So before running this program, let's see what's going to happen. A is 10 and B is 20. If A is equal to B, if 10 is equal to 20, it's not. That means this line is not going to run. If this is false, then what? Else, then this thing is going to run. Okay, so let's say I can also write another thing. Let me demonstrate that first. So I go to execute, compile and run and see what we get. There we have, these two variables are not equal because this condition was false. I could have written something like this. I'm going to discuss in detail how this if statement works in a future lecture, but since if A is not equals to B, I mean that's the short form of not operator. This thing, not operator, it just converts I mean, not if A is not equals to B, I mean that means this condition is going to be true because A is not equal to B, 10 is not equal to B. The result of this expression would be true, a boolean true. So we will get the same output as we did before. Let's compile and run this thing, and what we get is, because this statement did not run, this statement ran, because the reason is this the output of this thing is going to be false and the output of this condition is going to be true. So what we get is, because this thing is now true, that means this statement, which these two variables are not equal, that statement actually ran. So whenever you want to make some decision, let's say you are developing some kind of a hardware interface with some microcontroller, and that hardware might be some kind of a sensor. If you want to check whether that sensor output is so many volts, and do this. If this output is like greater than like so many volts or less than so many volts, and do that. So that's how we have to make decisions in programming. I'm going to revisit this if statement in lots of detail in future lecture, but coming back to our enumeration data types. So if s1 is equals to s2, what we did, let me recap what we did here, is that we have declared our own data type, user defined. They are behind the scene, they are essentially integer constants. So if you write enum semester, fall, spring, summer, we have defined our own data type, and they are actually behind the scenes integer constants. Let me explain what we mean by that. Then we declare two variables of type semester, and we name this variables as s1 and s2. Let's say if I want to declare two variables, what we did before, we just wrote a comma b. That means that we have declared two variables of type integer, and we can just assign the values later on. I mean, integers can contain like 0 and positive and negative whole numbers. Now s1 can only contain any one of these three numbers, or any one of these three constants. So s1 is spring and s2 is false. And let's say we want to develop that, we want to check whether that semester is equal to this semester. We can have I mean, if this thing is equal to this thing, I can just write C out. We can just write, okay, if they are same, we can just going to write same semester, and that's it. I mean, we can just have an L over here if you want to do that. Okay, but this condition is obviously not true, because s1 is spring and s2 is fall. This thing is not going to run. Okay, so the actual values defined in the enumerator list are known as enumerators. Let me spell it out for you. These things, these are, I mean, the list here, this list, they are known as enumerators. Okay, essentially they are ordinary integer constants. For example, I mean, the enumerators fall, spring, and summer that are defined for semester type could have been defined like this. Let me comment these things. For example, like here to here, I've commented that, and I want to declare a constant number. So what I'm going to do is constant. Let's say I want to declare a integer fall equals to 0. I want to make it a constant. That means it's not expected to change throughout the program, and whenever the fall name is used, that is essentially representing this 0 value. And I'm going to declare another constant integer winter. It's a customary practice to capitalize the name of the constants, because whenever you are reading some program or the code for the program, whenever you see some capitalized variable name, you can assume that it's a constant value if it's written by a programmer which is following this convention. Integer summer equals to 2, so that's another constant. So these values 0, 1, 2 are automatically assigned when the type is defined. These default values can be overridden in the enumerator list. For example, let's make another example over here. Let's comment that. Let's define another type. Let's say coin. Do we have coins for but what do we name those? Okay, a coin, and let's say we have penny equals to 1, comma, sorry, I think we should capitalize it, caps lock. Penny equals to 1, comma, nickel equals to 5. I think that's associated with the dollars, right? Dime is, I think, 10 cents, and quarter is 25 cents. Okay, end of statement. So that means that these names actually represents these integer values. So I could have, instead of doing this, I could have done like this. I could have defined a constant, sorry, C++ is case sensitive, constant integer penny equals to 1. So whenever the penny name is used, it represents 1. I can just write constant integer nickel equals to 5 cents. Whenever the name nickel is used, it means 5. And I can write constant integer dime equals to 10 cents, and constant integer quarter equals to 25 cents. I can just generate just like that. So I think I should have given some space over here, and that's okay. So that, they are essentially the same things. You can use this or that, it's up to you. C++ also give you a possibility that you need not to declare the values for these constants. If I write, let me comment that. If I write this type, month, and if I write January equals to 10, then I write February. Oh, sorry, I should have capitalized it, because it's not necessary to capitalize it, but it's a good practice. Okay, February, and March, April, May, June, July, August, September, October, November, and December. So we have assigned the value 1 to the first first enumerator over here. So what C++ compiler will do is that the enumerators which follow this thing are automatically assigned the consecutive values. That means that February would now represent 2, March would now represent 3, and so on and so forth. So if I want to let's try printing this. So if I want to see what the actual values are, I can just see out those things. I can just write see out and then just write January and see what we get over here. See, January would be and I could just write February or March, but the important thing is that behind the scene, January it represents a constant number 1. That's it. February represents a constant integer 2. March represents a constant integer 3. So if I multiply this thing by some integer number or anything, the result would be also an integer. So they are essentially integer constants, and it is possible to have several enumerators or several different enumerators with the same value. For example, I can have, let me comment this line as well. So I can have enumerator, let's say answer, that's a type, no equals to 0, false equals to 0. It is possible to assign the same numbers to different enumerator types. I mean, you can use no somewhere and you can use false somewhere, and they both will represent a 0 integer. And you can just write yes equals to 1 and true equals to 1. That is also okay, and okay equals to 1. So that means that, let's say someone, I mean, I just declare a variable integer answer or something like that. I mean, just to, and I take the input from the user, that what the answer for some question is. Let's say answer is this thing. So if I just check for the answer, I mean, that's I take the input from the user and check what the answer is. So if say if, sorry, I think I should write answer over here. If answer equals yes means 1. Okay, so if the answer equal, because I have to declare the, I mean, the user would be required to press 1, 2 or 3. So let's run this code and see what we get. If the answer equals to yes, I'm going to write cout, and I mean, I could have said you said it was okay. I mean, he could have pressed 1, he could have, I mean, he could mean yes, true or okay, and I could just treat them as 1, so no problem with that. So that means that these are essentially integers, constants, and nothing more than that. So I could just write and L. So I think that's pretty much it. Let me print enter answer to the question. Question would be anything, just write that and L, and cn, whatever the user enters over here would be assigned to ans integer, answer integer, and we will check whether that thing is equal to 1 or not. So yes, it represents just 1. Let's run this thing. Enter the answer to the question. Let's say I entered 0. Enter 0. It did not do anything because there was no condition to check. I mean, we did not do anything over here. We were only checking for if that thing is equals to 1. So I just press this thing and I just execute it again. And if I press 1, you said it was okay. Essentially, they are integers represented by names, and that's it. So I mean, do we need to further discuss it? So if the value of the variable answer is 1, then the condition will be true and this output will happen. There's another way to do that. I mean, if this thing is true, because we are checking for 1, I mean, we could have written, if the user pressed 1, that means 1 represents true, this thing will still run. I mean, let's run this thing. If I press 1, 1 is assigned to a and s variable, and this represents 1, and 1 is logically true. So this thing is a Boolean type here, happening over here. So this is 1, this thing is true, then this thing run. If this thing is false, whatever is in the bracket, this thing will not run, which comes after the if statement. So that means there are a few conventions, I mean suggested conventions to make the code more readable. I mean, I need to discuss it even more. I mean, let's go for the conventions. Uppercase letters should be used for constants because they represent constants over here. Similarly, you can if you want to declare your own type, I mean they are essentially constant really. So if you want to declare your own type, just capitalize the first letter here and use lowercase letters everywhere else. So that means that because the C++ standard data types, they are all lowercase letters. But if you have defined your own data type, make sure you just capitalize it. It's not necessary to do that. You can just name it using the standard naming conventions, but it's up to you. I mean, so that the code is more readable. Whenever we see a new data type which is not in the standard data type and we see that it's capitalized the first letter, that means that we can assume that it's a user defined data type, and they're behind the scene, they are essentially integer constants. So in enumeration types, they are essentially self-explanatory, so that the readers can understand better. We can just define something like this in just in the last few example. Day, for example, sorry, Sunday, Monday, Tuesday, Wednesday, and Thursday, Friday, Saturday. We can have enum radix. These are essentially base for different number systems, such as we have binary represents 2, base 2, and octal represents base 8. Behind the scenes, OCT just represents the 8 number, and these are just our ways of representing these numbers with names. That's it. 10 and hex is hexadecimal 16, and let's say we have a color, or we can just write violet, indigo, blue, green. Behind the scene, they represent just 1, 2, and 3, and 0, 1, 2, 3, something like that. So let's see, and we can have and so on and so forth. We can have in for example gender. I'm going to have male and female. Behind the scene, there just represents 0 and 1. That's it. So, oh sorry, semicolon over here. One more thing is that, let's say if I select this thing and copy it, or maybe okay, let's copy this thing over here. Okay, this list and this one over here might not be used in the same scope. We're going to discuss the scope in a separate lecture, what we mean by the scope, where the variables are visible, but we cannot say that oct equals to 8 and oct here equals 10 essentially, or maybe 9, I don't know about it. So it depends where it starts. January starts at 1, so 2, 3, 4, 5, oh it will be 10, so it will be 10. So we cannot use these same names in the same scope. By scope I mean, let's say if I'm writing a main program, so this main function, so all the variables, if you are declared over here, they are visible all over where the curly brackets limits are. I will explain the scope in a new lecture, but let's keep this thing in mind. And you cannot use the same name again if they are in the same visibility area. So visibility areas are enclosed by curly brackets. Going to just explain that in a future lecture. Okay. So another thing we need to keep in mind that the names here, I mean the enumerators, they should be legal. They should be like valid identifiers. I mean, just like you name the variables, keep in mind the same rules as you name the enumerators. So if I just write enumerator grade and I write A, then I write, is there a grade as A plus? Okay, might be. I write A, then I write A minus, and then I write B minus. Is that B minus or B plus? I don't know. Okay, B and so on and so forth, like B, and I mean this is not valid. I mean this is actually an error over here. The reason of error is because variable names cannot contain the special characters. So these special characters, this plus sign and minus sign, they are not allowed, so that will cause an error. Okay, so and enumerators can also be, because they are essentially behind the scenes, they're just constants, so they can also be anonymous. I can just write then you cannot actually declare them using the type name. I can just write enumerator I equals to 1 and V equals to 5 and X equals to 10. I mean they can be anonymous if you want to, but you cannot declare them later on. You cannot use the same type to declare and this kind of your own variable. So they are just a convenient way to define integer constants. So if I let's quickly, because I'm running out of time over here, let me check. I think this video is now beyond 50 minutes. So because as per rules we are only allowed to have a 40-minute video, so I think we are going to comment all of these things, or just comment everything here, and we're going to come here. Okay, let's quickly see out these things. See out, and this is a error here, so I'm going to comment that. See out, I'm going to write enumerators printing, and just write violet. Let's see what we get over here. There's an error here. Let's see what error is. Oops. Oh, I forgot the comma over here. Okay. Did I forget another comma? Oh yes, same types. This thing is saying you cannot use October over here. Let's write this thing as October_1. Okay, and then if we just compile and run, did we get another error here? DEC, I think DEC is also used here. Decimal, oh yes, okay, so just name this thing as decimal 1. Okay, enumerator is printing, and it has printed 0 over here because the first name here in the list wallet is 0, 1, 2, 3. And let's print the names of these things. Let's say instead of this thing I just print, and let me put some space over here, and I print January, and then I print February. Let's see what we get. I'm expecting 1 and 2, so put some space over here. So how do we put in space over here? We just write 1, 2, and then something like that. So space bar. Let's see. So I mean, they're essentially representing the integer constants over here. So execute, compile, and run. Let's see what we get. I'm expecting 1 and 2 over here, and that's Enumerators printing 1 and 2. Okay, so and the last thing, I mean, I can just use them. Let's say I just write integer a equals to February multiplied by 20. February is just a name which represents 2 here. So if I see out value of a is, and I just write value of a here, and L, I'm expecting, because if Feb represents 2 into 20 is 40, I'm expecting 40 over here. And let's execute this thing. There it is, value of a is 40. So enumerators are basically a way to define some constants, and those constants actually represent simple integers. Depends on where the list has started or what the values you have assigned that. If you haven't assigned any values, so these represents, they start from 0, 1, 2, 3, because here is male represented by 0, female by 1, wallet represented by 0, integer by 1, 2, and 3.